And welcome to lecture 6 in global biogeochemical cycles. This is brings us back to the kind of chemical aspect of the series of lectures. Don't think there's much housekeeping to report this week. The only thing I would draw your attention to is the email I sent earlier today. This is just regarding generally what approach we're taking towards the maths, but also what help you are and aren't entitled to regarding the current assignment, which assume you've all received this email. Okay, so as I say, we're moving back onto the chemical aspects of the biogeochemical cycles. Hope you all found Paul Connolly's water cycle lecture 2 weeks ago, okay? So this one we're going to be specifically dealing with sulfur, but as with all of these, there's links with the other biogeochemical cycles, and we'll find references to all these other cycles as we go along here. So today's learning outcomes, so we're going to start off it's going to follow a similar format to the others. We're going to be assigning the different chemical forms of sulfur, the different types of environment that it's in, what biological and any other processes the sulfur is subject to. Learning outcome, we'll be able to explain the processes, the magnitudes and the effects of the anthropogenic perturbation, so how much human activity has perturbed the sulfur cycle, but also in terms of how it might be mitigated. And then a big portion of today's lecture is going to be devoted to how sulfur affects the atmosphere and climate change in particular. So, this is sulfur, where it is on the periodic table. This is the elemental form of sulfur. It's a yellow solid, as S8 molecules. Just like to point out that the spelling of it, S-U-L-P-H-U-R, that's the kind of UK English spelling, but as Professor Van Dongen is very keen to point out to me, it's not the official IUPAC preferred spelling of it, so in a lot of sources you will see it spelled with an F. Those of you who are specifically working in chemistry, you'll probably be expected to spell it with an F. But you look at the IPCC report, spelled with a PH. Either's good as far as I'm concerned. Before I go on, now, just normally start most of the lectures like this. What forms does sulfur exist in? I'll just ask you, those of you that had already downloaded the PowerPoint, don't look ahead, or if you have already looked at it, pretend you haven't. What forms of sulfur can you think of that are important in the Earth system? Yep. Sulfides? Yeah, in the form of? Yep. So, yeah, sulfides in the form of minerals, yeah, pyrites in particular, yep. Sulfuric acid, absolutely. Get on to why that's important, yep. Sulfur dioxide, yep. Any others anyone can think of? Sulfates, yep. Again, that's a mineral form, but also in the form of seawater. So, I mean, yeah, you've basically covered the majority of the important ones, but there's a lot others besides that. Not going to give you the grand tour of this slide. This one's mainly as a reference, so you basically you can come back to if you're trying to look up what particular types of sulfur there are. One thing I would draw your attention to in this table, though, is the range of oxidation states we've got. Starting out with the most reduced form, which is sulfide. That's oxidation state -2, all the way through to the most oxidized form, which is sulfuric acid. Sulfur is a very active element, subject to a lot of redox chemistry, as introduced earlier. That's going to be a big theme of what we go through in this lecture. So, one of the features of sulfur is it's quite a reactive element. So if you you do find elemental sulfur in the natural environment, in the Earth. There's places in the Earth's crust where it exists as sulfur, but in this elemental form, it is very reactive. So one of the features of it is it does ignite and burn very easily. So it's an ingredient that's been used in matches. Also, it's a vital ingredient of gunpowder. It doesn't provide the actual power for the explosion. What it does do is help promote ignition. And also, like all the other elements that we're dealing with in this lecture course, it is biologically vital. Now, it's not quite as fundamental to organic molecules as, say, carbon, but what you do is you find it in some specific amino acids, and then, of course, these amino acids go on to form much bigger molecules like proteins and so on. And also, there are certain organisms where it's vital for their metabolic processes. Right. So the first part of this lecture, I'm just going to be going through the various forms of it and then onto the key processes. But first of all, start with the most reduced forms, and well, the most reduced and the most oxidized, I suppose, depending on the form of it. But the pool in the lithosphere. So there's a lot of sulfur minerals. Sulfur is one of the more abundant elements in the Earth's crust. And as pointed out earlier, one of the big forms of that is pyrite. So iron sulfide, which is this. That's an example of there. That's often referred to as fool's gold. It's a very abundant mineral in the Earth's crust. There are also other sulfide minerals as well. Copper and nickel are quite important. We'll get onto why in a bit. And then also you can get sulfate minerals. So gypsum, selenite. That's things like calcium sulfate. This is the opposite kind of chemical state of sulfate. This is the more oxidized form of it. And then that's in the form of precipitates or evaporites. And then finally, as I said, you get elemental sulfur in the crust. This is formed through redox. So what normally has happened is that there's some sulfur, a sulfur mineral has either been incompletely oxidized or incompletely reduced, depending on what its starting form was, to produce this store of elemental sulfur. So this is normally you've got presence of another element that's acting as the oxidizing or reducing agent, and it happens near volcanoes, hydrothermal vents, places where you've got hot temperatures. But it can also happen biogenically as well. We'll get onto that too. So those are the mineral forms. The other forms, as with everything, like to identify our reservoirs. So talking about the main reservoirs within the Earth system, first of all, we've got the lithosphere, the Earth's crust there, which I just talked about. Within the atmosphere, we can point to two different forms of sulfur in the atmosphere. We've got gases and we've got particulates. So sulfur can exist either in gaseous or particulate form. And we'll get onto these different forms as we go along. And then we've got the hydrosphere. That's where sulfur can dissolve into water. And then finally the biosphere. Anything living, or most things living, will have sulfur in there in some form. And that's locked up in the form of amino acids, proteins, etc. This is the kind of magnitudes we're talking about for the burdens. So this is in units of teragram sulfur. So we can see here we've got an absolutely huge reservoir in the lithosphere. Now the overwhelming majority of that will not be available to the Earth system. But then we have these other reservoirs here: ocean sediments, ocean, freshwater, soils and biota, and finally atmosphere. The thing I draw your attention to here, these numbers like these are going to keep cropping up throughout this lecture, and as always, these numbers are going to be different on different slides depending. That's just because not everyone can agree on this magnitude of the burdens, as I keep stressing. But I would draw your attention to the large range of burdens we've got here. We've got an absolutely huge reservoir in the lithosphere and a relatively tiny one in the atmosphere, but they're all very important. And then this is your typical, your typical simple reservoir model. So what we have here, this is our sediments crust burden here, and then we've got our atmosphere up here. But one thing I would immediately draw your attention to is what this particular one here, Stumman Morgan 96, is they've split the oceans and the continental sulfur burdens here. This is something you see very common in this in the sulfur cycle, is treating the oceanic sulfur cycle and the continental sulfur cycle as almost two completely different entities. That's because the governing processes are very different in the two different systems. Well, we have our usual things, so we've got weathering, we've got sedimentation into the crust, we've got movement between the continents and the oceans, but we've also got volcanic emissions, and then we've got all these processes that can take sulfur into the atmosphere and then also take it out of the atmosphere as well. But then finally we also have the anthropogenic perturbation here, which is taking sulfur from out of the crust and then adding sulfur to the atmosphere. I'm going to talk about this in more detail in a second, but as always, draw your attention to the magnitudes that we're talking about here. If you notice, the flux is here from weathering, deposition, sea spray there. All of these tend to be on the order of tens to hundreds of megatons sulfur per year. Now, megatons same as a teragram. So these are all on the order of hundreds. The anthropogenic perturbation here, as estimated in this in this plot, that's about 113 megatons sulfur per year. That is of a similar order to the estimated fluxes through the natural processes. So if you recall, in the carbon cycle lecture, if you looked at the anthropogenic perturbation to the carbon cycle, certainly in terms of in terms of carbon dioxide, the anthropogenic perturbation is actually quite small, but it is something that has built up and up and up over the decades and the centuries. Sulfur, on the other hand, we're talking the natural processes and the anthropogenic processes are more or less comparable in terms of the amount that they add to the Earth system. But of course, the anthropogenic perturbation to the sulfur cycle does not do it evenly. It's going straight into the atmosphere, for the most part. There's some exceptions. Okay, so this is, as with last week's assignment, starting off with the most basic. So, some of the kind of processes, we're going to start with the abiotic ones here. Now, a bit of a dense slide, sorry about this. This is just covering some of the processes that don't involve a biological action. So first of all, volcanoes. Volcanoes are very good at releasing sulfur. So any sulfur that's trapped in the lithosphere can be released. Now that can be in the form of sulfur dioxide or hydrogen sulfide, and that kind of really depends on what the chemistry of the volcano is. Now some of that is done through explosive eruptions, but about 70% of it is actually done through vents. Okay, it's not kind of your spontaneous releases. Seawater sulfate. Sulfate is a big component of seawater. It's already been touched on. If that ever gets into the atmosphere as sea spray, that will form particles as the sea spray dries out. Same with mineral sulfate in the form of wind-blown dust. Biomass burning. So the burning is it may be starting off as biomass, but it's an abiotic process, is setting fire to it. If it contains sulfur, the sulfur will oxidize very easily and it will form sulfur dioxide. And then finally we have processes by which sulfur can return to the lithosphere, much like with carbon. So we're talking sedimentation of insoluble forms of it. We've also got the hydrothermal formation of sulfates. You get seawater hot enough at high enough pressure and calcium sulfate will actually precipitate from solution. Evaporation of salt water. If you have an arid area and the salt water evaporates, this is a way of forming evaporites, which will include calcium sulfate again. And finally we've got the burial and fossilization of biomass. Now of course biomass is mainly carbon. You look at coal and oil. That's important from the carbon cycle, but as we'll see, it's also important from the sulfur cycle. Okay, so those are the abiotic processes. Things get a bit more complicated when we start to introduce biology, as it always does. Now, as I was saying before, sulfur is vital to most life as we know it, but most sulfur in biological molecules has to be reduced from the form it's available in. Most most organisms utilize sulfur in the form of sulfate. That's a very soluble form, and this is taking the example from a plant here. So we take sulfate, goes into the root, and then it's assimilated into the plant. Well, then it has to go through multiple stages of processing where it becomes reduced from sulfate to sulfide, so bringing it from its fully oxidized state to reduced state, and then it can start to form amino acids. So it starts out as cysteine, and then you can start to form other amino acids, and then go on to build up proteins and stuff. Yep. No. Good question. Answer is no. Unless you're a biologist, in which case I might say maybe, but no. For this chain here will not be covered in. I'll not expect you to know that in the exam. So, okay, perhaps should have been clear there. However, the details on the left, maybe. Who can say? So, but the key details is the plants or producers reduce the sulfur, incorporate it in order they can use it. But of course, much like with the carbon, and as we'll see, same with the nitrogen, it's the producers doing all the work here. Consumers, we're all consumers. We need sulfur, but we get it by eating other organisms. So the protein that's available from eating plants, other animals, and so on. That's how we get our sulfur. Now, that's not the only processes that involve sulfur in the biosphere. Sulfur can actually form the basis of some organisms' respiration. Now, I've covered aerobic and anaerobic respiration as far as the carbon cycle is concerned, but we have another process here, which is that certain organisms can actually utilize sulfate to oxidize sugar as part of their metabolism, as opposed to the relatively inefficient way of using the oxygen within the sugar itself to do the oxidization. That's the anaerobic process that produces methane. Covered that in the carbon cycle. This is a form where you take a sulfate and basically you reduce the sulfate and oxidize the carbon to release energy. So if you're one of these organisms and there's no so there's no oxygen present, but there is sulfur present, you can do this in order to kind of get some energy. One of the things it does do, though, is it produces hydrogen sulfide as a byproduct. You also do not necessarily, these organisms do not necessarily need to utilize it in the form of sulfate either. Through various mechanisms, it is possible to get this sulfur from dead biological matter as well. Now, if ever you smell rotting biological waste, now the example I've chosen here is the characteristic rotting egg smell. You know, eggs, they're full of protein, full of amino acids, lots of sulfur in there. If an egg goes bad, you smell it. That is the hydrogen sulfide. But that's also true of sewage, landfill, swamps, lots of other environments where you have anaerobic decomposition, where you have sulfur present. And then there's another process, which is that certain organisms are also able to use a sulfur-based form of photosynthesis as well. Not going to be covering this in massive, great big detail, but it's an interesting point. It's a different route to doing the usual photosynthesis that is done by, say, blue-green algae or plants, because this one does not produce oxygen as a byproduct. Now, some people think, it's not my field, but some people think that this may predate the oxic photosynthesis. But of course, if you're not producing oxygen, then it won't produce the same. It won't produce the same fossil record that oxygen-produced photosynthesis would. Other interesting bits of sulfur and biology is also when you have these environments here, like these hydrothermal vents, is that where you have a rich source of reduced sulfur, some organisms can engage in chemosynthesis. This is just basically the other reaction that I showed only in reverse, but this is a way of storing energy. So this is an alternative to photosynthesis. Now again, a lot of people speculate that this type of process predated photosynthesis as a way of organisms getting energy. And then some other people are also speculating that if you're ever going to have life on other planets, now the one that's usually singled out is Europa. That's a big water-filled, that's a water-filled moon of Jupiter. Could organisms using a similar process exist there? There'll be no light, it's completely ice covered, but who knows what's going on underneath this ice sheet. But then there's other thing that's important involving sulfur and the marine environment, and that is to do with phytoplankton. And that's in the photic zone. Now, phytoplankton are obviously very abundant in the oceans, but when phytoplankton die, they release a particular chemical. Now, I'm going to try and pronounce it. Dimethyl sulfonylpropionate. You don't have to worry about pronouncing that. That won't be in the exam. In fact, DMSP is not even that important as far as the Earth system is concerned. What's more important is what it gets turned into, which is this chemical here, DMS, dimethyl sulfide. I can pronounce that one. Dimethyl sulfide, that's a decomposition product of DMSP. I'm going to call it DMSP from now on. Now, that is very weakly soluble in water. So what happens is the DMS then, after it is produced, it then starts to go into the atmosphere. Now, there's that much plankton out there. That means that a biologically active ocean will produce a lot of DMS, and that's a lot of sulfur. So that's a major route from sulfur to get from the oceans to the atmosphere. There are other biologically produced molecules as well. So carbonyl sulfide, get onto that in the second half of the lecture. Carbon disulfide, methyl mercaptan. These are other ones that are also produced. Now, if you're going to do a big sulfur budget, you have to take account of these. But out of all of them, certainly in terms of fluxes, DMS is probably one of the most important. So, nicely segue on to kind of the processes governing the sulfur in the ocean. As I was stressing, most textbooks will treat the sulfur cycle in the marine environment and the terrestrial environment as pretty much two separate entities, and that also applies to the atmosphere as well. I mean, yes, you do get transport within the atmosphere from the ocean environment to the continental environment, but because the processes are that different, you will notice a difference in the behaviour of sulfur in the marine environment compared to the terrestrial environment. So this is just showing the marine sulfur cycle. So we may have touched on this already in a previous lecture, but if I was to say, what's the lifetime of sulfur in the ocean? So we've got burden here, 12 times 10 to the 20 grams. And those numbers there, and yeah, all of these values, all of these other values are in 10 to the 12 grams. Can someone just come up with a rough number for what you think the lifetime of sulfur is in the oceans? Now, also, I'm implicitly asking here that you remember how to calculate a lifetime. Yeah? Keep stressing that one. That one's important. Right, I think you said first, yeah? Go on, have a guess. Just order of magnitude. 325? Yes. 325 years? Anyone else? Do we have any other suggestions? Someone had their hand up over there.
I was going to say similar.
So. Right, and if we've got 12 times 10 to the 20 grams. Now, okay, easy one. How do you calculate a lifetime? Someone? Is your hand up or not? No? Yeah, go on.
This could be so wrong, but if you add up all the inputs and then divide it by just the burden.
Right, not quite. Yeah?
Solar sources, sun and six, and then it's something to
Right.
Like at time zero.
Right, I will just remind you, this is in the second lecture, but this one's important, so I'll keep stressing it. The lifetime for a given reservoir is the burden divided by the sum of the sinks. Okay? So that is just going to keep coming up, I can assure you. So, but if you can remember that one equation, that one will be handy. So 12 times 10 to the 20 divided by sum of the sinks.
Wouldn't it be 12 over 10 to the 20 divided by 96 plus 39 plus 43 plus that less than 6 plus 144? Wait, let's add it together.
Yeah, all times 10 to the 12 as well. No, but someone give me a rough number. So we've got all these numbers here. They're all on the order of. Well, I mean, what's the biggest numbers?
10 to the 8.
Yeah. So 10 to the 8. That's kind of, so you've basically taken your 10 to the 20 divided by 10 to the 12. Yeah. And then that's kind of 12 divided by. You know, we've got some hundreds in there, haven't we? So might want to take another order of magnitude off. Yeah. So of the order of 10 to the 7. That's what we should be looking at. That is tens of millions of years. Yeah? So, as a ballpark figure, yeah, if you want to get the exact number, then yes, we take this number here, we add up all our sinks, so 144, 96, 39, 40, 6, multiply them by 10 to the 12, dividing by that, and then that'll get you a more exact number. But yeah, we are talking order of tens of millions of years for. Now, so we've got this big pool of sulfate in the ocean. And the daft thing is that's not even the biggest reservoir of sulfur. You know, it's still small compared to the lithosphere. Okay, so this is just another one of these reservoir diagrams from a different source. It's not a particularly great graphic. The only reason I keep it is because this one actually has the turnover times written on there. So we've got our ocean, so the value here is 6.8 times 10 to the 6, so that's quite close to 10 to the 7. But then you can look at some of these others here. So in the marine atmosphere, lifetime is like 10 days. The continental atmosphere, 8 days. Reason it's short in the continental atmosphere is it rains more often in the continent. And then you've got this huge range of different lifetimes. So lakes and rivers, 3 years. Marine biota, 1 year. I think that's a little generous, that one, because some plants don't even last that long. Some biological material doesn't last that long. Then ocean sediments, we're back up to our 10 to the 6 years here. Lithosphere, 10 to the 8 years. That's hundreds of millions of years. Okay, so there's this phenomenally huge turnover time in some parts of the Earth system. So very big range of different lifetimes here. So then going over to the terrestrial sulfur cycle, the key processes here are very different for a number of reasons. First of all, the terrestrial environment has a very different type of organisms present. The producers are very different. We're not talking about phytoplankton anymore. And these also have a very different relationship with the lithosphere and the pedosphere. So here we get rather than assimilating the sulfur from the seawater around it, that's assimilated in the form of sulfate. But we have this pool down here within the lithosphere and the pedosphere, and what we're treating it here is just one big lump of metal sulfide. So we're talking about our pyrites, things like that. But there's processes by which we can get into this pool, but also back out again as well. So if you take one of these pyrites, you can dissolve it and reduce it to produce hydrogen sulfide, but then you can also oxidize it to produce sulfate. And then as soon as it's in sulfate, it can be taken up by the biosphere. But of course, eventually within the biosphere, it will get decomposed and it will remineralize. That's in the form of hydrogen sulfide again. That's through that decomposition process I gave earlier. We've got coupling between hydrogen sulfide and sulfate, but then also we've got this path here through the atmosphere where hydrogen sulfide can go into the atmosphere and be converted to sulfur dioxide, and then finally to sulfuric acid. So, but this whole kind of chain of sulfur, this whole, all of the different processes here, very different to what goes on in the marine atmosphere. So next few slides, just going to be going through a few specific processes of how the sulfur cycle interacts with the hydrosphere. That's in terms of how the sulfur can get in and out of the mineral phase. As I shown on the previous slide, you can form these metal sulfides, but then you can also dissolve them as well. So a lot of the time, the way it's going to get into the biosphere is if it gets into the hydrosphere stroke pedosphere, so in the form of rivers, but also in the form of groundwater. So you do have sources of sulfur, sulfate, natural sulfate. This is weathering of, say, for instance, if you've got pyrites, then these can oxidize to form our sulfates, which are a lot more soluble. Also get them from gypsum. You can also get input from rainfall. We'll get onto that in a bit. But then human activities can add to the content in rivers and groundwater. So air pollution, that will increase the input from the air. Mining. So that mining, if you're going to kind of take a load of stuff off the ground and then create a huge slag heap, or you're going to create a load of effluent, that can add as an extra source of sulfur to rivers and groundwater. That can have a serious effect. Erosion, so human activity increases erosion. That can also increase the chemical weathering. And the other human activities. I'm going to have to apologise there because I reordered the slides and I've just realised that one of them normally went before this one. It's now currently after. I'll get onto it though, I promise. Okay, so then we have these abiotic mineral interactions. So there's reactions in which we can form sulfides. So if we can have our hydrogen sulfide, and then the kind of end product can be our iron sulfides. So ultimately start forming our sulfur minerals. But then we can also go through these processes here, which convert our iron sulfides back to sulfates. And then also we have the different oxidation states of iron in play as well. So we can have iron conversion between iron 3 and iron 2. I'm not expecting you to know every single process here, but this forms the kind of basis of the chemical weathering. And then also we have our pyrite formation, so we can reduce sulfate. So we'll see here that this is taking biological material. This is the decomposition, and then forming hydrogen sulfide. This is our more anaerobic bacterial action. And then we can then combine this hydrogen sulfide with iron oxide to then ultimately form iron sulfide. So, and then there's a few other processes as well. So we can produce FeS2 from H2S when for having the ions, just the iron with one sulfur. And then also we can get this form here where it can react directly with inorganic, with the elemental sulfur as well. This is probably the kind of thing I would expect you to remember though, is that we have these various processes where we start with sulfur, sulfate, and organic matter at the top. We have all these stages that we can go through. So organic matter through bacterial action combined with sulfate, that produces a hydrogen sulfide, and then a hydrogen sulfide can then combine with iron minerals and so on, and then form pyrites. So this is a way of getting the sulfur back into the lithosphere. Partly abiotic, so there are some abiotic processes here, but there are also some biology involved in producing the hydrogen sulfide. And this doesn't just apply to iron sulfide, this will also apply to any other metal sulfides as well. So that's how we get it back into the lithosphere. And this doesn't necessarily apply, I should add this can apply to sediments of any description. It kind of depends on what the local mineralogy is like, how much oxygen there is and so on. So that's how we get it back into the lithosphere. Sulfur in the atmosphere. Now, as I say, about most of the second half of this lecture is going to be taken up with atmospheric sulfur processes, so these are obviously very important. Start off with the natural processes. As I said before, volcanic eruptions, very big source of sulfur to the atmosphere. But it's, as I said, the majority of the day in, day out emissions, these are from vents. And these kind of accumulate over time. But the big explosive emissions, they can release a large amount of sulfur at once, and they can cause very significant short-term climate perturbation. Be talking about this later, but this is one example here from 1815, when they reckon that had a very measurable effect on climate elsewhere around the world. It's not just the volcanoes, soil dust though, as I said, wind-blown dust that can contain sulfur minerals, so our sulfates and so on. Biogenic gases, so I talked about these before, hydrogen sulfide from the anaerobic decomposition, dimethyl sulfide, that's produced by the marine phytoplankton, and carbonyl sulfide, which I'll get onto in a bit. And then finally, anthropogenic emissions. One of the things I'd point out is that without human activity, generally speaking, the ocean is a bigger source of sulfur to the atmosphere than anything on land. So, and that is just basically because of the sea spray and DMS emissions. Okay? Without human activity, there is normally a net transport from the marine atmosphere to the terrestrial atmosphere of sulfur. So the marine atmosphere acts as a source of sulfur to the terrestrial atmosphere. With human activity, that trend has, on average, been flipped. So now, most human emissions of sulfur exist within the terrestrial atmosphere, so we burn most of our fossil fuels and so on land, and that has actually meant that the terrestrial atmosphere is now a net source of sulfur to the marine atmosphere. So what are these emissions? All right, I'm actually slightly ahead of time now. Okay, so anthropogenic sulfur sources. What the biggie, as far as anthropogenic emissions, is just through burning fossil fuels. Generally speaking, I highlighted this earlier, one of the routes for sulfur to get to the lithosphere is through fossilization of biomass. Or biomass contains sulfur. If we assume that there's nowhere for that sulfur to go when it fossilizes, then that means the fossil fuels will contain an amount of sulfur. Now, the petroleum industry, that will separate out the oil into different forms. Some forms of oil contain more oil than others. Generally, the heavier ones hold on to the sulfur more than the lighter ones. But left to its own devices, most fossil fuels will have an amount of sulfur in them. But they're not all the same, so there's different grades of coal. Talking about brown coal, that has a very high sulfur content relative to some of the other forms of coal, the hard coals, anthracites, that kind of thing. And also we have the option of removing the sulfur from the petroleum products. So when you see things like ultra low sulfur diesel, that kind of thing, that's had all the sulfur taken out for this purpose. But there is one other important source of sulfur to the atmosphere from the lithosphere that's down to human activity, and that is actually smelting. As I mentioned earlier, there's a lot of there are sulfide minerals other than iron, and the two I picked out were nickel and copper. Now, we don't use pyrite as a source of iron generally for our day-to-day iron needs. We tend to use the forms of iron oxides like hematite and so on. But for nickel and copper, both of which are in very high demand for electrics and electronics, we utilise them in the form of the sulfide minerals. And that just is a straight oxidation reaction to get at the metal from that. So we take our nickel sulfide or our copper sulfide, oxidise it, we're left with nickel or copper plus sulfur dioxide. These smelting plants, left to their own devices, produce immense amounts of sulfur dioxide in the process. So, and then there's other human activities which add to sulfide. Biomass burning. So if you burn any trees or so on, the trees still contain sulfur, or any other biological matter for that matter. If you burn it, the sulfur in there will get converted into sulfur dioxide. There is also situations, much like methane, where if there's any situations that encourage anaerobic decomposition, they can often produce a lot of H2S, so hydrogen sulfide. So classic examples would be landfill sites, the kind of stench you get off those. One of the ones that's particularly interesting is if you ever have gypsum in the form of drywall. If that is ever mixed in with general landfill, then you've got a very large source of sulfur there, because that's mainly made of calcium sulfate. So you have some decaying biological material in the presence of a lot of sulfate that will actually produce a lot of hydrogen sulfide. Now, this sulfur source is not that important from in a global budgeting perspective, but it can be important from a local air quality perspective and a local groundwater quality perspective as well. And then the final one, which I just had to add on there out of completeness, is SF6. But we kind of covered this one in the carbon cycle lecture, even though it's not got any carbon in it. SF6, it's a synthetic molecule. It's highly inert, so it doesn't participate in any of the other sulfur cycles. Once it goes into the atmosphere, it just kind of stays there for ages. It's also a big greenhouse gas. For those reasons, it's actually handled alongside the CFCs, as we discussed in the carbon cycle lectures. So I won't really be talking about that one here. Okay, so these are the ways of getting sulfur into the anthropogenic methods of getting sulfur into the Earth system. You'll notice that they all, or mostly, send them straight into the atmosphere. Can anyone, without looking at the slide ahead on the PowerPoint, if you've already got it, can anyone just give me a few examples of ways we might mitigate this? Yep.
Isn't there a way to kind of make fuels cleaner?
Yep.
Like use cleaner
Yeah. So use lower sulfur fuels. Yeah. Yeah.
And you use chemicals in the chimney itself to like scrub it away.
Yes. Indeed. Yes. So take the sulfur at the point, and take the sulfur out at the point of emission. Yeah.
use less transport and
Okay. Yeah. That's the easy answer. Is actually do less of the activity. Yes. I suppose I've got to give you that one. Yeah. So yeah, cleaner fuels, chemical scrubbers in chimney stacks. So this is an example of a scrubber system. So the general purpose of a sulfur dioxide scrubber is basically you want to convert the sulfur dioxide into sulfuric acid. So that's in a form that you can capture it in and then maybe use for something else. There are lots of applications of sulfuric acid out there, and this is actually, these kind of scrubbers is one of these major ways of actually producing sulfuric acid as a chemical that we can use. But these have only been in kind of general common use, certainly in this country, since about the 1980s. Use of cleaner fuels, yeah, you can take the sulfur out of petroleum products. And using better quality coals. So one of the things you can do is reduce, if you can't eliminate coal completely, then you can maybe replace the use of brown coals with hard coals, for instance. And then also there are ways of mitigating the release of hydrogen sulfide as well. One of the things if you ever take rubbish to a tip that will make you separate out your construction waste from general waste, that is precisely for this reason, is that you don't mix in, you don't get any gypsum in contact with any decaying biological matter. And you can do things as well, stopping any landfill sites getting too wet. You can treat waste to try and prevent the biological activity, or, and you can, this applies to methane as well, you can try and trap the emissions as well. So I think I'm going to finish the first half 5 minutes early. This is just a kind of a summary. Again, these are These are some more fluxes, don't necessarily agree with the previous one. These are kind of taken from an earlier version of the course, one of the recommended course textbooks. But this is just to give you the idea of the general fluxes. This is the kind of modern fluxes we're talking here. And again, I'd like to point out, we've got this factory here. This is our anthropogenic emissions. So like the kind of in 10 to the 12 grams sulfur a year, 93, and then transport to sea, 81, and then transport to land, 20. So if we were to take away the anthropogenic perturbation, we'd be talking about the transport to land would probably be kind of similar, but the transport to sea would be much reduced. And you can see here, most of these marine processes here, they're not directly perturbed by anthropogenic activity. So I think that takes us up to the break. We're 5 minutes early today. Does anyone have any questions at this stage? We're going to be moving on to atmosphere and climate in a second. Yes?
I was wondering, we talk about using like atomic masses.
Yes.
Will we get a periodic table in the exam, or do we just need to know them?
I will. Right. If you need to know any atomic weights, they will be on the exam scripts. If you look at any past papers, they should all have that. I'm not going to ask you to memorise atomic weights. That would just be cruel. Yeah?
You've shown us like at least, I think, 2 different models with like different numbers.
Yeah.
Which would you prefer we knew?
I will tell you, right, if you're talking about the exam, I will tell you which version of the numbers you need to know. Okay? I am not asking you to memorise these numbers. I've asked you to kind of appreciate the magnitudes and so on. Okay? I am not going to ask you to remember the numbers simply because the best minds in science can't agree on which ones are best. It's that simple. Okay? Okay, so 10 minutes back here for the second half. Oh. Hi.
Alright, it's not really an answer. I'm just getting very confused by the wording of the question. So, this one here, it's more to do with the Excel. What does it mean? Like change the model so the appropriate force is a 0 for 50? Because it's like, I've been looking and some of it's like, the ones to do with marine are like 39 and 11. So that's 50. I'm wondering like, what do you then we need to check? Like it's just the Excel sheet, right?
Right, okay. I will emphasise right. All I'll say here is the emphasis here is that all of the sinks you've been working with so far have been first order sinks.
Right.
Okay? Now, if you go to the definition of a first order sink and a zeroth order sink, you have to find a way of changing it such that it behaves as a zeroth order sink as opposed to a first order sink.
Okay, I think I get that.
Right, so
anything to do with marine, change to 0.
no, just that. No, it says change the model so that the appropriate flux.
Appropriate flux.
So I'm not going to give you too many hints on that.
I understand that.
So all I'll say is think of which processes are the one by which you get carbon changing its form in response to productivity.
Okay, so I'll draw a diagram and do arrows and see which one.
Well, there is already arrows on there.
It's one. Yeah.
Yeah. Yeah.
This is after the time, the normal time.
Yeah.
The system will become around 64% closer to the new equilibrium.
Yes.
But this does not mean that it's approaching the new equilibrium.
Well, it is approaching there. But if you go back to this, right? So over time it gets closer and closer and closer and closer to the right. Mathematically, it never reaches the equilibrium, but after every unit of time, it gets 68% closer to the equilibrium.
If I want to know how long will it get to the new equilibrium, this time is not the responsibility. If I want to know like this.
Yeah, well, but it represents the ability to adjust to a steady state after a sudden change.
So one question asked me how long will it take to approach the new equilibrium. So this is not the time.
I'm not going to answer the question in the assignment. Okay? No, I'm not going to answer the question, but all I will say is that the maths for that question is contained within. It was part of that lecture. Okay? I'm not going to give you the answer to the question if that's what you're asking me, because that's effectively what you are asking me. So I'm not going to give you the answer there. Yeah. No, but what I can do is, if you have any questions about that particular lecture, I can answer those. I'm not going to answer the question in the assignment. Okay?
Without human effect, electric force cause sulfur from sea to land. If it's with human
Well, with human effects, so going back to this one, so if you see the human effects, that puts a big source in the terrestrial atmosphere. So there's a net transport of sulfur to the sea from the terrestrial environment. Yeah? If that source wasn't there, then the transport to the land, then there would be more transport to land than there would be transport from the land to the sea. So the net flux would be from the sea to the land, not from the land to the sea.
Oh, you mean the direction is changing?
Well, not so much the direct, because the sulfur is going in both directions. But the net transport, so one minus the other, would be different. Yeah.
I just want to ask you about the second question. About this part, can you estimate what the new equilibrium is like? Did you want us to identify the precise moment when the system will reach the equilibrium?
No.
I'm really confused the way
Good
questions are structured.
Right, okay. No. Okay, that one does deserve clarification, actually.
The following
No,
as
what
well.
I should have said, no, that's a good question. The new equilibrium burden.
The new equilibrium burden.
That's a very good point there, actually. It's ambiguously worded.
It's really ambiguously, sorry about that.
No, it's fine. No, because, you are absolutely right. What I will do is clarify that one in an email.
And what is it meant by this sentence as well? is the time taken to approach the equilibrium constant of system's turnover time? It's okay, turnover.
Right, I will. The only thing I'll say there, and I'll put this in the email as well because you're not the first person to ask.
Okay.
Refer to earlier lectures.
I just want a clarification. Is this 2 referring to points, or is a part of logarithm?
Oh,
'Cause
it's the logarithm of the
okay.
number 2. No, I think you may have actually. I may have to issue a clarification there as well. Actually. That's a
Also,
good point.
how do we do that with Excel? How do we?
It is the command is just log.
Is this the command of just like?
I'll tell you what. I shall. No, these are all good questions.
I've got more.
Well, yeah. Okay, we'll see.
I think I'll just email you.
No.
I
Well,
was the
yeah.
guy who emailed
Oh,
you.
you are excellent. Excellent.
Because
Excellent.
I'm absolutely struggling. I don't know what to do.
Well,
Even tried changing this module.
No, I've got to say actually, all I'm saying is, don't worry, you're not the first person to
I'm really.
be intimidated. Now, the thing is, the maths here is
It's
generally.
I understand. But
yeah.
the thing is, I don't understand what the question is asking me.
Right. Okay. No, what I can do, I can certainly do a clarification on the question.
Please.
Yeah, I think because you're not the first person to ask as well, so.
Not properly looked at the other ones, but as a.
Right. Well, I will issue a clarification on those.
Okay.
Yep. So. And right, so the question you had was
This one.
it should be equilibrium. That's right. Okay. See, the problem is, you see, is I have to keep changing the questions every year.
Yeah.
So I can't. Yeah, it's my job. I know. So unfortunately, every now and again, something's ambiguously worded. What I can do is issue a clarification on the wording. The bit there says, is the time taken to approach the zero consistent with the system's turnover time?
It's okay.
I'm not going to explain that one. That one you have to refer to lectures. That one, however, I think I will issue a clarification on how to put that in Excel. Because there wasn't explicit instructions on how to do that there, so I will put that in.
So once you calculate the turnover time, you compare that with the equilibrium.
That one I'm going to have to direct you to the lecture notes on. That's part of the question. To tell you more than that would be giving you the answer.
Okay.
I can refer you to the.
I looked at lectures and honestly, they're very confusing. I mean, the thing is that, okay, there are equations, but I would appreciate if there were units stated and stuff like that.
Units.
Units and meaning of letters and everything, all the equations.
Well, okay. Well, if you're having trouble understanding the equations and stuff, please just drop me an email and I'll try and issue a clarification. Because it's not my intention to baffle you like that. If it is just a matter of units or something, then I can do that. That's not a problem. Okay. So I mean, I do try to include these things in the notes, but if there's something not clear there, just let me know. Okay. Okay, I think ready for the second half. Okay, just so as you're aware, there's getting a couple of questions about the assignment. There are one or two things which it's been pointed out could have been worded slightly better, so I will be issuing a clarification over email on one or two things. Okay, I'm not going to talk about them here and now, but expect an email on those. Okay, so sulfur in the atmosphere. Okay, so this is just a kind of a general overview. Not going to be going into this in massive, great big detail, but I'm going to be talking about, this is a kind of overview of the processes that I'll be talking about. Now, some of this is not just involving the processes by which it gets into the atmosphere, but also a lot of the transformations that can occur within the atmosphere. So going between different chemical forms, but also going between different physical forms as well. Once you put sulfur in the atmosphere, a lot of the forms of sulfur are reactive. They will change forms, but they'll also change from gases to particles, and then will also influence things like, they'll also influence things like clouds, climate, so on. Okay, once you get some sulfur in the atmosphere, if it's in the form of a gas, the main way of getting it out of the atmosphere is the formation of sulfuric acid. So sulfuric acid is, that's the oxidation state of that is 6. It's one of the more oxidized forms of sulfur. The general trend of oxidation of sulfur is towards the more oxidized state. And then, so once it is in the form of sulfuric acid, then that's when you can start to lose it from the atmosphere. Lifetime about 1 to 10 days. Sulfuric acid, it will stick to most things, so if it's presented with a surface, then it will deposit onto that. That's known as dry deposition. But it's also highly soluble, so it will get into the ocean, it will get into the water table, but it will also condense onto particles very readily. Sulfuric acid does not like existing as a gas very much. Okay, so sulfuric acid is one of these forms that will readily form secondary aerosols. Talked about in the carbon cycle lecture. So, main loss mechanism from the atmosphere is through rainout. Talked about it again in the carbon cycle lecture. That is basically when it rains, that's a way of getting rid of particulates of the atmosphere. So, talking again order about days there. Now, before it goes into the particle phase, though, if we emit it, say, in the form of sulfur dioxide, it's got to undergo some chemistry before we can turn it into sulfuric acid. Same also applies with all these other forms, so DMS and so on. Sulfur dioxide, but one of the main routes is if you can convert any of these other forms into sulfur dioxide first, which can then subsequently turn into sulfuric acid. But then also some of these other forms can convert into these other sulfur compounds. They're not as important in terms of burdens, but they are for certain processes. So DMS as well as sulfur dioxide, we can also turn it into these other forms. This is methane sulfonic acid, DMSO, carbonyl sulfide, and then we can also produce carbonyl sulfide from these other forms as well. Well, let's, for the sake of argument right now, we'll say that most of it is converted to sulfur dioxide. And then, in order to convert that into sulfuric acid, that is with reaction with the OH radical, which is, again, this is one of the main oxidants in the atmosphere, talked about in the carbon cycle lecture. I'll talk about it some more in the nitrogen lecture as well. But it's a simple matter of reacting with the sulfur dioxide, initially forming sulfite species, so that's going from oxidation, going up one oxidation state, but then a second reaction will convert it into sulfur. A second and third reaction will convert it into sulfate, and then a sulfuric acid plus sulfite to sulfuric acid. This reaction is not one of the fastest reactions on the planet. So this whole process here to get from sulfur dioxide to sulfuric acid, that will normally take on the order of days, depending on the lifetime there. You're talking about, days to a week, so on, depending on how much OH you have present. As I say, most sulfur species have a lifetime of around days. The exceptions are carbonyl sulfide and SF6, but I'm not going to talk about SF6 here. But carbonyl sulfide is an interesting one. This one, it's not one of the biggest ones in terms of burden, but it has an anomalously long lifetime compared to the other sulfur species. That's because it's got this very unique structure here, where it's got a double bond between the carbon and the sulfur. Now, you do sometimes see this written as in two different ways, OCS or COS. Some chemists like calling it COS because they stick to the convention that the carbon should always come first when they give the molecular formulas. But others write it OCS because that's kind of closer to what the molecular structure is. As far as I'm concerned, both are right, okay? I'm not going to ask you to do any one of these ways. What I would point out, though, is the molecular structure is very similar to carbon dioxide. So it's quite chemically it's quite stable, but also plants, it will also get taken up into plants in the same way that carbon dioxide is. That is just simply because the stomata are designed to take up carbon dioxide. They will also take up carbonyl sulfide as well, kind of almost by accident, I suppose. It's got other losses as well, so it can be oxidized in the troposphere, but the reaction there is very slow. can be hydrolyzed on the sea surface. It can be transported up to the stratosphere and then oxidized up there where the oxidation's much stronger. But generally speaking, most of these processes are quite slow. Tropospheric lifetime, you're talking of the order of about 5-6 years, as opposed to 5-6 days, which is like the other forms of sulfur. So, okay, we've got our sulfur. We've converted it into sulfuric acid. Then what? Sulfuric acid, as I say, it has a very low vapor pressure. So I talked about vapor pressure water, or Paul Connolly talked about vapor pressure water. The vapor pressure of sulfuric acid is very low. It does not like existing in the gas phase. So what it will do is it will condense onto particulates. Now it can condense as neat sulfuric acid, which is a liquid under normal conditions, but what you often see is it will react with basic salts. So sulfuric acid, so this example here is reacting with ammonia. So ammonia, which will quite happily exist as a gas, that sulfuric acid will react with that to form bisulfate, but then it can even take up an extra molecule of ammonia to form ammonium sulfate. So that's 2 ammonias for 1 sulfate. Sulfuric acid, it's also a very strong acid to the point that it will actually displace other acids if it finds them in particles. So the example taken here, we've got an ammonium nitrate. As we'll talk in the nitrogen cycle lecture, this forms a lot of nitrogen particulates. So this is from the various atmospheric forms of nitrogen pollution. So we have our ammonium nitrate there, but we show it this sulfuric acid molecule, and then what happens is that it forms ammonium sulfate and it kicks the nitric acid back out into the gas phase. So it will form ammonium sulfate from ammonium nitrate. So what I'm saying, and this is true of other aerosols as well, it will also kick hydrochloric acid out of a chloride aerosol. What this means is that sulfuric acid really doesn't like existing in the gas phase. You make sulfuric acid, you can pretty much think of it as going straight into the particle phase. It's also the reason why if you take the remote atmosphere, if you go far away from your pollution sources, the aerosol tends to be sulfate dominated rather than nitrate dominated as well, because you produce this sulfuric acid over the time scale of days and it's kicked out all your nitrate. Talk about that some more in the nitrogen cycle lecture. So this is our sulfuric acid, and this is how you make particles from the sulfuric acid. So once sulfate gets into the condense phase, so it's out of the gas phase, it's in a particle. Now, for the sake of argument here, we're treating it as if it's in solution, because there's normally a little bit of water present in these particles. This is very analogous to the carbonate system that I talked about in the carbon cycle lecture. So we start out with our sulfuric acid here, but if we make the aerosol more neutral or more alkaline, then it will convert through bisulfate through to sulfate. Now the equivalent salts here that I'm giving, the equivalent solutes for these kind of different acidities. So if we've got our sulfuric acid here, and then using the the ammonium system here, so we've got ammonium bisulfate here, and then finally through to ammonium sulfate, which is under a bulk solution will be pH neutral. So the state that the sulfate exists in, much like carbonate, this is kind of moderated by the pH. And so the form, it's dictated by what else is present. So in the case of seawater, we have things like sodium, chloride, potassium, all these other ions, carbonate being one of the big ones that moderates the pH. And so that means that within seawater, all of the sulfur 6, which is what all of these are, oxidation state 6, all of the sulfur 6 is in the form of sulfate. It's alkali, there isn't any bisulfate or anything, it's all sulfate. Not necessarily true of particles in the atmosphere. If there isn't enough ammonia to balance it, then what will happen is you will start to form acidic particles. Now, this can happen in very polluted environments. If you've got a lot of sulfur in the atmosphere, you start to form sulfuric acid. and there isn't enough alkali to balance it out, and then you start to get acidic particles. Also happens naturally in the marine environment. You have this large source of sulfur in the form of dimethyl sulfide. This ultimately gets converted into sulfuric acid, but of course the marine atmosphere does not have as much source of ammonia, so therefore your marine particles also tend to be quite acidic as well. Should also add that another interesting process is when you have sulfur interacting with cloud particles. I was saying earlier, sulfur dioxide, that one of the processes by which you can get sulfur dioxide forming sulfuric acid, that is when you react the sulfur dioxide with OH radicals to produce your sulfuric acid. But I say that's not a particularly fast reaction. However, sulfur dioxide is also water soluble, and so if you have a cloud, the sulfur dioxide will dissolve into your cloud droplets. And what this will form is your sulfite forms. So this is sulfur 4 oxides. So bisulfite, HSO3, and SO3 2-. These are slightly less oxidized forms of sulfur. But then once we have once it's dissolved, we can then participate in some chemistry. One of the big ones is one of the ones that we have to consider is ozone. Ozone will dissolve in water as well, quite happily, and that will oxidize sulfur 4 to sulfur 6 through this process here. So we just add an ozone, and that turns our sulfite into sulfate. Also, there's a process that's been getting a lot of attention in recent years as well, is whether you can also do that with nitrogen dioxide in polluted environments. And for very polluted environments, let's say with a lot of pollution, so the example that was originally speculated on was Beijing. It's whether you have enough nitrogen dioxide present that can also cause this reaction to progress here. Now, in theory, these are very fast reactions, but they're also self-limiting. These reactions here, the ozone and the nitrogen dioxide reactions, they get slowed down by the presence of acidity. So if you're making sulfuric acid with these reactions here, then as the more and more sulfuric acid you make, the more and more sulfur 6 makes, then the more acidic the solution gets, and then these reactions slow down. Well, then we have this other reaction here involving hydrogen peroxide. So hydrogen peroxide, this is another atmospheric oxidant. You get it in the presence of water vapor, OH. If you've got some of that present, and hydrogen peroxide is very soluble in water, so if you have a cloud, pretty much all of the hydrogen peroxide will dissolve into the cloud water, then you get this other reaction taking place here, which is basically just combining sulfite with hydrogen peroxide to produce sulfate and water. This reaction is also very fast, but it is not limited by pH. So this one can just keep producing more and more sulfate as you go along. Now, just couldn't resist putting up a bit of history here. This is a paper from 1990, but you might notice that this is one of the kind of older experiments that what at the time was the UMIST atmospheric physics group was involved with. You might notice that there's a few names on here, such as Gallagher and Chillarton. These are some of the historic measurement. This is some of the historic science that our group was involved with. This is long before I started, by the way. But the likes of Professors Gallagher and Chillarton are still with us. One of the things that they did was to show that if you've got a site here on top of a hill, what can happen is if you've got a hill and the air is coming towards the hill, then sometimes the air will have to, depending on the shape of the hill, will have to actually is forced up the hill just by the shape of it. And of course, how to make a cloud. If you're pushing the air upwards, the air goes upwards, it cools down, and you can form a cloud, and then you form what's known as a cap cloud under this circumstance. So if you see a hill that's just got this cloud sat on top of it, that's this exact process here. There's this particular site in Cumbria, radar station, that's particularly susceptible to these. And what they were able to do is set up some instruments upwind of the hill, so measuring what's going towards the hill, and then set up some measurements actually inside the cloud itself, and then seeing what the cloud water was doing. And then one of the things they're able to show is that you take all this material going into the cloud, and then you compare what's actually being formed inside the cloud, and then you can show that there's actually a lot of what they're able to show was that inside the cloud droplets you're producing a lot of this sulfate, and it is through these cloud processing reactions. The upshot of this, so instead of this reaction where we're talking kind of days, weeks to produce sulfuric acid from sulfur dioxide, this is using the OH radical. Instead, we're bringing this down to the lifetime of minutes within certain clouds. If you've got enough hydrogen peroxide present, then pretty much you can get most of your sulfur dioxide converted pretty much straight away to sulfuric acid. You look at the atmosphere as a whole, if you look at total budget, we reckon it's probably the dominant mechanism for getting sulfate in the atmosphere, sulfur 6. And then, of course, once it's in the cloud droplets, it will stay in the cloud droplet. There's a number of things that can happen. One is the cloud droplet can get rained out, and then rain out a cloud droplet, that's transfer into the hydrosphere or pedosphere. But it might not rain out. What might happen is the cloud may dissipate, the cloud droplets dry out, but what you're left with is where the cloud droplets were, you'll be left with aerosol particles. In this case, the aerosol particles are going to have a lot of sulfate left over. They'll have more sulfate present than what they had before they went into the cloud. So what you get is a very effective way of building up this sulfur on these cloud process particles. And it's not just the sulfate, you can also get methane sulfonic acid through this as well. But this is one of the main routes for getting sulfur into the particle phase. So, that's how we get the sulfur in the particle phase. And then this is how it has one of the big effects on the environment. If I was going to say what are the kind of big effects that sulfur can have on the environment, what would be your first answer? Yep. Sorry? Able to cool. Yeah. Able to cool climate. Acid rain. Yeah, that's another one. Those are the two big ones, basically. Well, they're the kind of main ones that people care about anyway. Sulfuric acid and MSA, the particles that they make, they tend to be these, the secondary particles. They tend to be these accumulation mode particles that may have been referred to already. These are the particles that are less than 1 micron in diameter. Now, particles of this size, they're not really big enough to simply drop out of the sky. So the main loss mechanism for those is rainout. These can persist in the atmosphere for quite some time, you know, talking days, weeks, or possibly even longer, depending on where they are. The other thing about sulfate is it's a very effective cloud condensation nucleus. Now, this should have been covered in the lecture that Paul Connolly gave, but in that lecture is saying that different aerosols, larger aerosols make more effective cloud condensation nuclei, more effective at forming cloud droplets, but also ones that are formed of soluble material. Sulfate is very soluble. Or at least sulfate in the form of ammonium sulfate is very soluble. And also, when it rains out, that's a way of getting it directly into the hydrosphere. So similar to the nitrogen cycle, we're going to be talking about that next week, if I recall. But then sulfate also has this very interesting property called, referring to it here as nucleation. As I said before, sulfuric acid does not like being in the gas phase. And if you get enough of it being produced, it will keep trying to condense onto the particle, onto whatever particles it can find. But if it does not find any particle to condense onto, eventually it will start to condense onto itself. So we've got our condensable vapor. This nucleation can apply to a few different systems, but if we've got our condensable vapor here, once there's enough sulfuric acid being produced, so you've got all this sulfur dioxide, say, and you keep producing more and more and more sulfuric acid, at some point the sulfuric acid just basically says, right, enough of this, I'm forming new particles. And then it forms these particles, they're about 1 nanometer in size, and then once you initially start forming these particles, then all of the sulfuric acid will try and condense onto these ones. So what can happen is that these can just start growing bigger and bigger and bigger, so start off at about 1 nanometer in size, and then quickly grow into tens of nanometers, even hundreds of nanometers, but they can also coagulate with each other, or more material can condense onto them. And then eventually they're going to get to the kind of sizes of particles that we really care about if we're trying to look at the effect that these have on clouds. And that's kind of on the order of about 50 to 100 nanometers. So, kind of summarize the whole thing here. Now, this is not a straightforward process. Probably the most successful atmospheric scientist in Europe built his career on studying this, basically. So I'm not going to go into too much of the details. But you will also hear the phrase new particle formation sometimes. Kind of, if you want to get technical, new particle formation is a bit more all-encompassing than nucleation, but they kind of mean the same thing. So what we have is this spontaneous formation of particles. Now this happens when something like sulfuric acid does not have enough particles to condense onto. If you have lots of particles already there, it won't happen. So it will condense onto the particles that already exist, and it doesn't occur. But if you have if the number of particles you have already present aren't sufficient, that's when you get it occurring. And it's not just sulfuric acid, there are other things as well. Not covering these in great detail, but there are other things that will also do it. Certain organic molecules, when they react to produce secondary aerosols, some of them can exhibit nucleation. That's a very recent discovery. It's also known that iodine will also cause nucleation as well, but that's only emitted in very specific areas. But it will also occur when you have a very large source of sulfur. So by that we're talking volcanoes, power plant plumes if you don't use scrubbers, even if you do use scrubbers but the scrubber's not removing anything. When you have this very concentrated source of sulfur as well, that is when you're producing a lot, even though the reaction is slow, you can be producing a lot of sulfuric acid still, simply because you have so much SO2 present. So the kind of places you observe this occurring tends to be when you have a big source of sulfur, or when you're in a very remote atmosphere. Now, the reason you see it in a very remote atmosphere is because you don't have very many aerosols present, but if you're still producing sulfuric acid, then you're still producing this sulfuric acid that wants to condense onto existing particles. And then this is what it looks like if you make some measurements of it. Now, this plot here, this was taken in Pittsburgh, if I recall. Now, this is an area that was very strongly affected by some power plants. Now, this shape here, this graph this is one of the ways which scientists look at particles in the atmosphere. Basically looking at how many of these particles there are and how big they are. Now, those of you that have done the certain other modules on the atmospheric measurement laboratory may have already seen something along these lines. But for the benefit of those that aren't doing these courses, basically what this plot is showing, this is just time on the bottom, time of day. This axis here is the size of the particles. So we're starting out at kind of like 3 nanometers on this plot. And then if you go up here, this axis here, we go to 10 nanometers, 100 nanometers, and then approaching a micron up at the top of this plot. And then what this is showing on the plot is how many of these particles you've got. So as the day progresses from about kind of 9 o'clock onwards, all of a sudden, where it's red, is we have a lot of particles of these very small sizes, so about 10 nanometers. But then as the day progresses, so we go through from 12 till 4 in the afternoon, all these big particles, this big large number of particles here in the centre of this graph, these are occupying particle sizes that are getting bigger and bigger and bigger. These particles have the kind of appearance of growing. Now, this type of plot actually has a name. When you see this pattern on this graph, it's referred to as a banana. Not my choice of name, but that's just what people call it. But it's when you see this very characteristic behaviour where you see these new particles being formed. They start out at very small sizes, but then start to grow to bigger and bigger sizes. And you'll notice as you get to later on in the day, so you know, about kind of 12 a.m. midnight, they've kind of grown. They're kind of pushing the sizes, in this instance, about 40, 50 nanometers. That, under certain conditions, that's when they can really start to participate in cloud processes. That's when they can start to form cloud droplets. And the other thing I would point out is that after we do get these big, huge numbers of particles, we stop getting the really small particles being formed. The reason for that is that once you do start forming these huge numbers of particles, these particles present this huge amount of surface area to the sulfuric acid. So that will act as something for the sulfuric acid to condense onto, so it will stop forming new particles then. And then once you are forming these particles, they'll keep growing as you make more sulfuric acid, but also if there's anything else that wants to form particulates present, so any secondary organic carbon, any ammonium nitrate, providing you've got enough ammonium, that sort of thing. So there's all these other things will start condensing onto these. They'll get bigger and bigger, they'll start to coagulate, and then eventually we get to the sizes that we care about for cloud formation. And then this is just a kind of like a overview of the processes that I talked about. So we have our nucleation down. So we have our gases to begin with. So I start at the beginning. We have our gases. Now, as I keep stressing, there's all these other gases out there. It's not just sulfur dioxide, but a lot of these gases do get turned into sulfur dioxide. So we're starting here with our sulfur dioxide. Now, within this cloud here, that's not an actual cloud. I'm just trying to indicate that these are gases. We can form sulfuric acid through reaction with OH, or we can go into a cloud droplet and form our sulfuric acid or sulfate through reaction with these other oxidants. And then what can happen once we have our sulfuric acid is it can condense onto a cloud droplet, it can condense onto an aerosol particle, or it can nucleate. But when we get nucleation occurring, the ultimate fate is growth, be it through coagulation or more condensation. Eventually these particles will get bigger, so these nucleate particles, eventually they're going to turn into aerosol particles. These aerosol particles, these can become cloud droplets, so that's the activation process that's covered in the water cycle lecture. But then these cloud droplets can also become aerosol particles again if they dry out, so evaporation again. And then what we're left with are these particles here within the atmosphere on the order of about 100 nanometers up to about a micron. They're not really big enough to simply just fall out of the atmosphere very easily, so these kind of accumulate in the atmosphere, and then this is what's referred to as the accumulation mode. If you ever hear people talking about accumulation mode aerosol, that's kind of what they're talking about. But then of course, one of the main loss mechanisms, as I said before, is if you get them into a cloud droplet and then you get rain, or if you get rain falling through an aerosol, that can also sweep out the particles as well. So this is a kind of the overview of what happens to the sulfur once it gets into the atmosphere. And then we're on to the bad stuff. So yes, as correctly said earlier on, one of the big things that we care about with sulfur is acid deposition. So a few pictures of what can happen. Within Europe, acid deposition is not seen as big as an issue as it used to be. Now, this was a huge issue in the 1980s, a huge issue within Europe. It also created a lot of big diplomatic problems as well. Britain used to be very reliant on coal-fired power stations, but of course all this sulphur was being emitted in the atmosphere. It had to go somewhere, and a lot of the time where it went was Scandinavia, and that caused massive problems for the Scandinavian forestry and fisheries. It was causing damage to trees, also causing damages to aquatic life as well. The pH of the rivers and the lakes was going down, and it was actually causing problems for fish to spawn. This is, like I said, this was a major issue in the 1980s, and of course, for a while, Britain refused to admit it was a problem, but eventually they kind of agreed to limit the amount of these emissions. We've now got a protocol, an international protocol on countries exporting and importing pollutants to each other. One of the big ones for that is sulphur pollution, and of course, what's happened in Britain since then is that we've installed the scrubbers into our power stations, so they're producing less sulphur, but also generally relying less on coal power as well. So as time has gone on, and as in later years removed the sulphur from vehicle fuels as well. So this is less of a problem in Europe than it used to be. However, there are lots of other parts on the planet where this is still very much an issue, where this deposition of sulfuric acid is very much an issue. Another problem of increasing atmospheric sulfur through the product, now this is entirely because of the nucleation effect, is you don't just get more particulate matter, you also get a larger number of particulates. So it's not just particulate mass, it doesn't just increase, say, PM 2.5, and it's also increases the number of aerosol particles. And I should say, comment I made earlier on, not entirely true. People do care about PM 2.5 within urban environments. Sulphur does contribute there. Just realise that for Earth system science, what we care about is the atmospheric deposition and the cloud interactions. And also optically thick hazes as well. The particles get bigger. That means the hazes get thicker. That means the atmosphere becomes whiter. Increases the atmospheric albedo. Now there's a few other kind of extra effects that it can have. So reduces the atmospheric lifetime of insoluble material. That's because if you can coat insoluble things like soot with it, and that means that it's more likely to get into cloud particles as well. And so I've just talked about the acid deposition, so it has big effects on ecosystems. Also, it enhances the weathering of carbonate minerals. So what that can do is convert carbonates to carbon dioxide. But also an example here, given of a statue that's had a bit of a run-in with some acid deposition, is showing over the years, so you've got a statue made of marble, that's a form of carbonate. Is it made? No, sorry, limestone. And then over the years, you can see that the facial features of this statue have been completely removed. One thing I would say though is that sulphur is rarely a problem for nutrient provision though. Most of the time the thing that we care about, it is an essential nutrient. Most of the time the thing we care about though when we talk about eutrophication is nitrogen or phosphate. That is because they are more likely to be the limiting nutrients in a given ecosystem. So to take the example of the marine ecosystem, there is more sulfate there than any biological organism really knows what to do with. So marine ecosystem is never short of sulfate. And most of the times in the aquatic terrestrial systems, it's not very common for it to be sulfur limited. It is normally nitrogen and phosphorus limited. But what it does have is a big effect on climate. So, first of all, now I think this figure's already been shown, but I'll recap it again. The effects on climate what we really care about is the balance, is the energy balance. So energy of the sun going in versus energy of the earth going out. Now, aerosols, just aerosols in general, not just the sulfate ones, but the organic carbon aerosols, the nitrate aerosols, dust, everything. They can all increase the atmospheric albedo. So if you have a haze, so if the atmosphere is visibly whiter because there's a lot of aerosol there, what that will do is reflect sunlight back to space. That will cause a cooling effect. But then aerosols can have a much bigger effect on climate by modifying clouds. Clouds are very white. They reflect a lot of heat back to space. But they can also reflect heat back down to the earth as well. But this figure here, excuse me, this is taken from the 2007 IPCC report. This is taking the example of an unperturbed cloud, okay? So normal cloud, not doing anything, not been changed by any human activity. So we've got all these cloud droplets here. One of the first things that might happen, if you increase the number of aerosol particles in the atmosphere, which sulfur pollution can do, is that may increase the number of cloud condensation nuclei. You increase the number of cloud condensation nuclei, that increases the number of droplets within the cloud for a given amount of water. Okay? So you've got the same amount of water distributed over a larger number of droplets. What that means is you have a large number of smaller droplets. In that circumstance, the cloud, it becomes thicker, becomes whiter, becomes better at reflecting light. It increases its albedo. So what happens is if we increase the number of droplets, then more sunlight gets reflected back up to space by the clouds. But then there's other effects as well. If covered last week, the formation of drizzle in clouds. So that's when you get droplets bumping into one another and forming cloud droplets. They form more efficient drizzle if the cloud droplets are bigger. Now, of course, if we've got a larger number of droplets, the individual droplets are smaller for a given amount of water. That means we get less drizzle. So we get this drizzle suppression. That means the cloud will stay whiter for longer. So that's another reason why we'll get more light reflected back up to space. So that also increases the height of the cloud, but won't go into that in great detail. So these are all mechanisms by which sulfur can cool climate, and it's remarkably efficient at doing so through these mechanisms. And one of the things that you'll often see is, I don't know how much individually you'll have covered in terms of this in meteorology, whatever modules you're doing, but one of the more common clouds that you see in the Earth's atmosphere is this one called stratocumulus. Now, probably see a lot of this in Manchester, but this is where you get some very low clouds that kind of completely cover the boundary layer. And by the boundary layer, we mean the kind of lowest 1 kilometre or so of the atmosphere. This is what they look like from above. They're these kind of fluffy, fleecy clouds. They can produce drizzle. Most of the time they don't. But they just present this big white area to the sun, and they are very good at reflecting light back to space. But also, because they're quite close to the surface of the planet, they are also strongly influenced by whatever is emitted near the surface of the planet. So if you're going to put pollution in the atmosphere, it's these types of clouds that are going to get affected first. And then finally, these clouds are also very warm. So they're also good at radiating. Because they're so low down in the atmosphere. That's why they're warm, and they're also very efficient at radiating the energy upwards as well. And these are very important to considering climate. So these are just like some typical amounts of typical outputs from a climate model. Won't go into any massive great big detail, but this is considering the amount of clouds on the atmosphere. But the end product they're looking at when they do a modelling exercise such as this is the net radiative cloud forcing. What that means is we talk about the net forcing of clouds, units watts per square metre. So this is the same as we talk about the forcing on climate by carbon dioxide in watts per square metre using the radiative model we covered at the start of the module. And then this is how much this forcing is distributed around the world. See, clouds are very heterogeneous. They don't affect the planet as a whole. What you can see is the output from this model is you'll see there's big areas of the world which are this kind of blue colour. That means that the forcing, the kind of perturbation of these clouds is having a cooling effect on lots of different parts of the world. Should also add that there are a few locations where you can see these little red dots here. That's up nearby the poles. Those are locations where the perturbation to the cloud is actually causing a positive climate forcing. That's where it's causing warming, but it's very localized warming near the poles, near the north and the south poles. But then in order to understand this, it's absolutely key that you get the cloud droplet numbers right. And it's predicted that this whole nucleation process is absolutely vital to understanding this. Now this is from a paper from about 10 years ago. This is trying to predict the effect of how important is nucleation to cloud droplet numbers. And we can see here that what they've done is try to produce a map of this is the percentage of cloud droplets that are coming from nucleated particles. And then this is a map of the percentage of particles coming from primaries. Now by primaries, this is what talks about distinction between primary aerosols and secondary aerosols. Primary aerosols being the ones that are directly emitted to the atmosphere. We're not producing them through secondary processes. By this token, all nucleated particles are secondary. So what I draw your attention to here is for the primaries graph here, it's a map of the world showing how important the primaries are. You see there's this big splodge here on the Southern Ocean. That is pretty much all sea spray. Okay, there's some very strong winds in the Southern Ocean, drives a lot of sea spray into the atmosphere. So most of your cloud droplets in that part of the world are formed from sea spray. And then you get these other parts of the world, so where we have Africa here, Central Africa, we've got South Asia, East Asia, Europe. You can see in the Americas there's various blotches there where there's these big hotspots for where we have primary particles. These are anthropogenic primary particles being produced. But then you can see here, in the certainly in the temperate oceans, but also the Arctic Ocean, we've got these big hotspots here where all of a sudden these nucleated particles are the most important. Now these are the one. Now you'll notice that these are all over. These are mainly over the marine environment. Now, as I was saying earlier, a lot of people consider the marine environment separate to the terrestrial environment. This is all not. This is mostly not coming from anthropogenic sources in the marine environment. This is coming from the DMS that's being produced by the plankton. So that's a big natural source of these things. But that said, you can see that there's certain continental environments where it's important as well. So, for instance, Siberia, Canada, so on. And then wrap that up all together, we've got these important processes going on here. And sulfur does have a cooling effect on climate, as we can see on it. This is from the most recent IPCC report. So I've shown this before, where we've got a warming effect by black carbon, but we also have a strong cooling effect by sulfur as well. Now, the aerosol perturbation to climate is divided into two parts. The top part here, this is the direct radiative interaction. So this is hazes, this isn't forming clouds. But then on top of that, we got the cloud adjustments by aerosols. Now, two things to point out here is the net effect of aerosols. The cloud perturbation effect is generally thought to be bigger than the direct perturbation effect. And most of this cloud perturbation effect is being driven by sulfur, we reckon. But the other thing I would point out is if you look at the size of the error bars on these plots here. The cloud perturbation effect, the error bar is massive. Okay? The climate forcing potential is somewhere between minus 1.33 to 0.06 watts per square meters. That is huge. and it's something that's, you know, been frustrating scientists a long time, is not really been able to make that error bar get much smaller over the years. People are trying them. But you compare that to, say, the level of uncertainty on, say, carbon dioxide, which we think is relatively well understood, and methane and so on as well. This is like represents some of the biggest uncertainties in climate science at the moment. Should point out then as well that for the negative climate forcing, okay, so all of the cooling agents, sulfur is the biggest man-made influence that we're aware of. This is followed by organic aerosols, which is this little brown section here, but sulfur-based aerosols, through their direct effects and also their cloud perturbations, it's the single biggest anthropogenic global cooling agent there is. But of course, I was pointing out, it's not just an anthropogenic cooling agent. Could it be a natural cooling agent as well? Well, it has been posed. This, you may recall from the first lecture, that talked about Gaia theory. So are there these natural feedback processes that can counteract climate change? This is one of said processes. Now this one's known as the claw hypothesis. The reason it's called claw is the C-L-A-W is the surnames of the scientists on the paper that proposed it, the L being Lovelock, he of Gaia theory. Idea here is that if you've got a warming scenario, you might increase the amount of biological activity in the oceans. That might increase the amount of DMS being produced. More DMS being produced by the oceans. More DMS in the atmosphere. More DMS in the atmosphere. That means more sulfur dioxide, more sulfate. More particles, more cloud droplets, more cooling. And then that could mean that you have there and then a biological feedback mechanism. And that was one of the proposed mechanisms of homeostasis as part of the Gaia hypothesis. I say was. Over the years, this particular hypothesis has tended to fall out of favour. Basically, there's very little evidence appearing that this is actually happening. And there could be loads of reasons for that. Could be that the biological activity isn't increasing in response to warming, it's nutrient limited, say, or that we're just not producing the amount of particles needed to make a difference. So I'm just going to finish up. So far I've talked about the troposphere. I'm going to move on to the stratosphere now. There are sulfate aerosols in the stratosphere. In fact, there's a discrete layer up there known as the Young layer, where you get this kind of peak of sulfate particles, altitudes at about 20 kilometres up. Now, there's various ways of getting the sulfur up there. One is the carbonyl sulfide that I talked about earlier. That's got a long enough lifetime that can transfer to the stratosphere and then convert into sulfate. But then it can also transfer to the stratosphere and then not convert to sulfate, get transferred down again. So it's not necessarily the biggest source up there. More than that, though, if you ever get an explosive volcanic eruption or really vigorous weather system, that can transfer the sulfate up there as well. And you put some aerosols up there, they have a long lifetime. You don't get as much rain out in the stratosphere because it's not like you do in the troposphere. So they can actually persist up there for quite some time. So much so that it's actually quite a well-established fact that if you get a very large explosive volcanic eruption, that you do normally see a period of a few years after this eruption where you expect to see some warming. Now, for the big eruption, there's this graph here taken from the NASA website. That's for 5 eruptions that we have good data for, and it's just taking an average of the global temperature after the eruption. And it's because you're injecting all this material into the stratosphere, not just sulfur but also some ash, and it's causing a bit of global cooling. Effect is kind of relatively minor, and it's quite temporary as well, only lasts for a few years. But it's thought that when you get a really, really, really big eruption, now we're talking supervolcano, there's geological evidence for there's proxy data, sorry, that the last supervolcano eruption at Yellowstone Park caused cooling for nearly a century. And then that takes us on to the subject of geoengineering. We know what volcanoes do. If we want to cool the planet down, could we do it deliberately? So we have the technology, in theory, to put sulfur in the stratosphere. and people are seriously looking at this, whether it's a case of doing balloons, rockets, aeroplanes. Someone here is proposing this humongous tower, which I think is frankly bonkers. But the most feasible thing they're talking about, by the way, is using aeroplanes to disperse it up there. Could you cool down global warming with that? Hypothetically, yes. There's actually a paper came out earlier this week. This arrived just in time to sneak this into the lecture. Very much an active area of research. These people think it's feasible, can be done, and they reckon they could probably cancel out about half of global warming using this. Of course, the big problem with this, of course, as well as unintended consequences, does not get rid of the carbon dioxide in the atmosphere. If you stop applying this cooling technique, the carbon dioxide is still there, you'll warm back up again. Also, doesn't help with things like ocean acidification as well. So I think with that, unless there's any questions, that's that. As I say, if any of you have any further questions about the assignment, please email. I won't give you the answers, but if there's any clarifications on the questions or anything else, I can provide answers over email. Other than that, next week... Oh, has everyone had the scanner? Sorry. Where is the scanner? How about that? Okay, if you could bring it... if someone could bring it down here, and then anyone else use it on the way out. Okay, so reconvene next week for the nitrogen cycle. Yep.
I want to know what is the CCN
Of the rain?
Yeah, like
It can vary. Because last week, sorry, go on.
so I collect the rain and bring them to the lab.
Yes.
And try them.
Yeah.
And put them under the telescope.
Yeah.
And see it.
Well, you might not see it, because if the CCN is something like a sulfate salt, and you dry it out, all you'll get is a salt residue. You know, you won't necessarily see the original CCN. So for instance, if you take your rainwater, and rather than drying it out, if you analyse it using, say, ion chromatography or something, then you will find there'll be a lot of sulfate in there, and a lot of that is from the aerosol particles.
Chemical reaction.
Yeah, from the chemical. Well, so you form the sulfate. You either form sulfate aerosol, or you form sulfate in the cloud droplets, and then this will be incorporated into the rainwater. Yeah, and then you will see that if you analyse the rainwater. Does that make sense? Does that answer your question?
Kind of.
Okay.
Because I don't really understand the two things.
So the two, which bits don't you understand?
No, just leave this with you.
Yeah. Thank you very much. Anyone else need it? It's over.
I don't understand the chemical reactions between different forms like
Okay, well, you're talking about the conversion between... So you're talking about how the sulfate is formed, or the conversion between sulfuric acid, sulfate, bisulfate, that. Right, right, so when it's forming between... This is the... this relates to the pH. You know, as described in the carbon cycle, so the acidity of the the solution. So if you have a more acidic solution, then the sulfur will combine with hydrogen ions to form sulfuric acid. If it's less acidic, then it will dissociate from the hydrogen ions and form sulfate instead. So it's to do with how many hydrogens it acquires. Now the same is true for carbonate, because I covered this in the carbon cycle lecture. It will also be true of the nitrate and the phosphate as well. So it's going to appear in all of these. Now, if you don't think this is clear,